Welcome back to the Tech Talk podcast, where we dive into the fascinating world of technology and software development. Today, we're exploring a crucial topic for building scalable and robust applications, the actor model of programming. If you're keen on concurrency, distributed systems, or just want to keep your applications running smoothly, you're in the right place. Let's dive right in. The actor model is a programming paradigm that helps manage concurrency within a single process. You might be asking yourself what that really means. Instead of directly managing threads, which can lead to complex issues like race conditions, locking, and deadlocks, the actor model encapsulates logic into what we call actors. Each actor serves as an individual client or entity functioning as a little unit of work with its own local state. The beauty of this setup is that the state isn't shared with any other actor, which helps to avoid many of the pitfalls we often encounter with shared state in traditional multi-threaded programming. So how do these actors communicate? They send and receive asynchronous messages. This means that when one actor wants to send a message to another, it does so without waiting for a response. However, it's important to note that message delivery isn't guaranteed. In some error scenarios, messages can be lost, and the actor model is designed to account for that. Now let's shift our focus to scaling. In distributed actor frameworks, this message passing mechanism is key to scaling applications across multiple nodes. Whether the sender and recipient are on the same node or different nodes, the actor model remains consistent. If they're on different nodes, the message is encoded into a byte sequence sent over the network and then decoded on the other side. This seamless transition between local and remote communication is one of the standout features of the actor model. But here's where it gets interesting. When you're running multiple versions of your application across different nodes, compatibility becomes crucial. If you want to perform rolling upgrades, gradually deploying a new version of your service to a few nodes at a time, you need to ensure that messages can be sent between nodes running different versions of your application. This is where backward and forward compatibility comes into play. Let's break this down a bit. Take Akka, a popular actor framework, for instance. It uses Java's built-in serialization by default, which unfortunately doesn't support rolling upgrades. If you want to upgrade your application, you might need to switch to a more flexible serialization method, like protocol buffers, which makes rolling upgrades easier. On the flip side, you have Orleans, another actor framework that employs a custom data encoding format, but also lacks support for rolling upgrades. Upgrading requires setting up a new cluster, migrating traffic, and then shutting down the old one. Similar to Akka, Orleans can utilize custom serialization plugins. Now, let's talk about Erlang OTP. This system is designed for high availability, but making changes to record schemas can be surprisingly challenging. While rolling upgrades are possible, they require careful planning. An experimental data type introduced in Erlang R17 may simplify this process in the future, but for now, developers need to tread carefully. So why is data encoding so important? It affects not just efficiency, but also the architecture of your applications and your deployment strategies. When deploying an application, particularly in a rolling upgrade scenario, you want to ensure that all data flowing through your system is encoded in a way that maintains compatibility. This means that new code should be able to read old data and vice versa. Let's take a look at some common data encoding formats. Programming language-specific encodings often limit you to a single language and frequently lack compatibility. Textual formats like JSON, XML, and CSV are widely used, but their compatibility can be tricky. They come with optional schema languages that can either help or hinder your efforts, so you need to be cautious about data types. In contrast, binary schema-driven formats like Thrift, Protocol Buffers, and Avro offer compact, efficient encoding with clearly defined compatibility semantics. These schemas can also aid in documentation and code generation for statically typed languages. However, there's a catch. The data needs to be decoded before it becomes human-readable. Now, where do data encodings come into play? They're crucial in several areas. First, in databases, the process writing to the database encodes the data, while the process reading from it decodes it. Second, in RPC and REST APIs, the client encodes a request, the server decodes it and encodes a response, and finally, the client decodes that response. Lastly, in asynchronous message passing, nodes communicate by sending messages to each other, which are encoded by the sender and decoded by the recipient. So what's the takeaway? With careful planning and consideration of data encoding, achieving backward and forward compatibility and rolling upgrades is entirely possible. This not only allows for rapid evolution of your application, but also makes deployments less risky. Frequent small releases become the norm, reducing the chances of a faulty release affecting a large number of users. In conclusion, the Actor model provides a powerful framework for building scalable and resilient applications. It simplifies concurrency, enhances communication between components, and with the right strategies for data encoding and compatibility, it allows for smooth upgrades and evolution of your software. Thanks for tuning in to this episode of the Tech Talk podcast. If you found this discussion helpful, don't forget to subscribe and share it with your fellow developers. Until next time, may your applications evolve rapidly and your deployments be frequent. Catch you in the next episode.